Okay, welcome back everyone. So last time we looked at the Thevenin equivalent, and there's a second equivalent circuit that's a simple circuit, and it's called the Norton equivalent. And the Norton equivalent has a parallel structure here. There's a current source pointing towards the top terminal or the positive terminal of our network. And then we have a parallel resistor here that's given the names IN for Norton current and RN for the Norton resistance. The reason it has to have this structure is if you remember when we turn off the sources, when you turn off a current source, that means you open it. So when I open this source, basically that path goes away, and I can see that the equivalent resistance then is just the Norton resistance. If this were in series here instead of in parallel, then it would, looking into the circuit, when we open this up, it would be a resistor and then an open and then back to the other terminal. And so that would be infinite resistance because it'd be an open. And so that wouldn't satisfy the resistance that we would need to have the same characteristic as any just given linear network. So it must be in this configuration, our current source in parallel with the resistor, and for the Thevenin one, for similar reasons, we had to have the voltage source in series with that resistor. And so just a little bit of background there. You don't really have to need to know that, but it's kind of good to know from like a designer point of view. What are we going to do for this Norton equivalent then? Remember, we're trying to find an IV characteristic here that matches a given linear network, and to simplify it so that this circuit gives the same IV characteristic as that linear network. And so to do that, we have to match our open circuit voltage and our short circuit current, because those are the parameters that we are using to define the characteristics. And so what we're going to do for the Norton equivalent structure is we're going to write equations for the open circuit solution for the open circuit voltage, and then also find the short circuit current in terms of Rn and In, and then we can then reverse that and solve for Rn and In in terms of the open circuit voltage and the short circuit current. And if we can do that, then we can find values for Rn and In that would match any given linear network characteristic. So this is our general equation for a characteristic equation. I is m times v plus b. We want to find m and b in terms of In and Rn, so we can write an expression there that matches any other given linear network. And then we also want to find In and Rn in terms of VOC and ISC, so that we can solve for those when you actually solve your linear network. In terms of VOC and ISC, then we can get the values for In and Rn. So that's what we're doing here. So let's go ahead and go through our process. So we've solved the open circuit. Here's the open circuit. It's all marked up with the nodes, and I've written an expression for the open circuit voltage because that's what we're interested in here, right? So open circuit voltage is just going to be VB minus VA. And then we look at our node voltages, 0 on node A, and node B we didn't know, so we can write a KCL. The KCL here, we have negative In coming in, we have VB over Rn coming out, and then there's nothing down that path, so it's a really simple expression. And if I solve for the node voltage B in terms of In and Rn, we get this. VB is In times Rn. And so VB minus VA is our open circuit voltage. So solving for the open circuit voltage, we just get In times Rn. So that's our first expression. The open circuit voltage is In times Rn. And so now for the short circuit solution, and in this case we're looking for the short circuit current. So again, I've kind of marked this all up and I've drawn the node. This is interesting, is that there's actually only one node in this short circuit solution here. And because the short kind of introduces a interesting situation. So to solve this, we actually have to look at this in a little bit of a different fashion. Instead of, this is called a distributed node, and we're gonna also look at like a specific point junction. And so point P is kind of the point I'm looking at. So we're going to look at the current entering and exiting point P. As you can see, if we write a solution like that, we want to find out what ISC is, and that's the current that's exiting point B to the right. So we're going to write that KCL right there. So into, I'm going to look at it all going out like we normally do. So out of point P this way is negative IN. Out of point P this way is going to be VA minus VA over RN. And then out of P this way is going to be our ISC. So that is our three terms in our equation for KCL, and that's equal to 0. One thing you'll note here is that VA minus VA is 0. So that whole term goes to 0. And I'm just left with negative IN plus ISC equals 0. And so that you should be able to see there that the short circuit current is the Norton current. So when we short this, you might have heard that the current goes through the least resistive path, and so this is more resistive than the short. The short is essentially zero resistance, and so all of that current is going in this direction, and so IN is equal to ISC, and nothing is going through that path. So now we have it. So ISC is IN, and from the previous page, VOC is INRN, so we've solved generally for our short circuit current and our open circuit voltage for this structure. And so now we can look at how this relates to a general characteristic equation. So this is our general characteristic equation for any linear network. If we know the short circuit current and our open circuit voltage, we can write the characteristic equation as I is negative ISC over VOC times V plus ISC. In this case, we have specific ISC and VOC for this structure of our circuit. And so substituting in there, I can see that negative ISC or VOC is negative IN over INRN. INs cancel out. This is negative 1 over RN. And so that is the term right there for the Norton equivalent. And then ISC is I Norton, and so we can just substitute there. So this is the equation that we have for the Norton characteristic. I is 1 over the Norton resistance, negative slope. And that makes sense because this is a conductance, and we want that to be conductance multiplied by our voltage. And then we have a current here, and that's just the Norton source current. And so there we have it. So if we find values for IN and RN such that they satisfy these two expressions, then they will match the characteristic equation of the circuit we're trying to find the equivalent of. And so we're ultimately trying to find the values for IN and RN in our circuit. And so if we solve for the short circuit current, open circuit voltage, and rearrange these two equations, then we get this. So IN is ISC, RN is VOC over ISC. So this is kind of the end of our lesson in terms of what you need to do for a Norton characteristic. So you go through all the stuff we've previously done, find ISC and VOC, and once you have those, then you use these two equations to solve for the values of IN and RN, and then you build this circuit with those values, and you found your equivalent, okay? I want to just extend this a little bit and just show you a comparison to what we did with the Thevenin characteristic. So here was the equation that we determined last lesson for the Thevenin characteristic, and we have our Thevenin expressions, V Thevenin is VOC and R Thevenin is VOC over ISC. Notice that VOC over ISC is for R Thevenin and VOC over ISC is for R Norton. So these are actually the same exact values. And so whether you're using Thevenin or Norton, you can find, once you find VOC over ISC, you have the resistance for both. So that's the first note we have when we're comparing these two. The second thing is if you look at IN is ISC, and if I kind of rearrange this equation, ISC is VOC over RN, and so IN is VOC over RN, but RN is also RTH, and VOC is also VTH. So I can rewrite this to say that if you want the Norton current, it's the Thevenin voltage divided by that resistance that they both share. And likewise, if you have the Norton current, you can multiply it by the resistance of Thevenin or Norton, they're both the same, and you get the Thevenin voltage. So it's pretty easy to transform these two circuits equivalents between each other. If you have the one going to the other is really simple, just using these expressions right here. All right, so let's do a Norton example. You guys should be getting pretty familiar with doing these node voltage solutions for the IV characteristic, finding VOC and finding ISC, because we've been doing that in each of these lessons. We're going to do it one more time here. So I have a circuit, has a 30 volt voltage source, has a 1.5 amp current source, and then we have various resistors here that complete the circuit, and here is our port. And we're gonna look at the characteristic at this port. So in this first solution, I'm doing the open circuit, and I wanna find open circuit voltage. And so here it is, and I've labeled all my nodes A, B, C, D, and E. And you can see the solution for the open circuit voltage then will be VE minus VA. One thing that's of interest by inspection, I can see that this 5 ohm resistor leads nowhere, and so there can't be any current through it in this situation. And so we can see that VD and VE must have the same value of node voltage, since there's going to be no current through that resistor. And so that makes my solution simpler. Node voltages, easy ones, 0 volts for A, 30 volts for B. We don't know these three yet. We have to use KCL. So writing the KCL for C, we got VC minus 30 over 30, VC minus 0 over 20, VC minus VD over 10. And so I have those three terms there. That's all equal to 0. Write the KCL for D. I have VD minus VC over 10. I have 1.5 amps entering, so that's negative 1.5 amps leaving. And then I have VD minus VE over 5. And I already had said that there's going to be no current through that resistor there, so I can just drop that term. So there's going to be 0. You can also see, since that VD and VE are the same, that's going to equal 0 as well. So I've solved those two expressions simultaneously, and I got 30, 45, and 45 then for my 3 remaining unknown nodes. All right, great. So now we know all the node voltages. How do you find the open circuit voltage? I know open circuit voltage here, we said it was VE minus VA, VE minus VA, so that's 45 minus 0, so that's 45 volts. I found the open circuit voltage, 45 volts. Now, that would be the Thevenin voltage if we were using the Thevenin equivalent, but we're not. But we're still going to be able to use this in solving for our Norton quantities. Second step in these solutions is to find the short circuit solution, so we can find the short circuit current. And so here's the short circuit on the load, on the port, and I've drawn all the nodes. This time the node A wraps around to both terminals of our port, and I'm looking for the short circuit current, and I've written in an expression that short circuit current, we have to look at this in terms of, KCL. In this case, the current going through the 5 ohm resistor also continues out that port, and so that is the value we're finding. So I can use this 5 ohm resistor to calculate that short circuit current as VD minus VA over 5, and that's what I'm going to do. So write down our easy node voltages, 0 volts and 30 volts, just like before, and then I don't know C and I don't know D, so I have to write KCLs for that. C, VC minus 30 over 30, VC over 20, VC minus VD over 10, those three terms equal to 0. At D, VD minus VC over 10, we have 1.5 entering, so we have negative 1.5 leaving, and then VD minus VA over 5, but VA is 0, so that's just VD over 5. And so I've written my second expression, all those currents add up to 0. Using these two equations in a solver, I solved simultaneously for VC and VD, and we get 10 volts and 8.3 repeating volts for both of those nodes. So we want to find the short circuit current. So from above, we have VD minus VA over 5. That's just 8.3 repeating over 5, which gives us 1.6 amps, 1.6 repeating amps. And so we know our short circuit current now, and we know our open circuit voltage. So we have everything we need to write our characteristic equation, or to find our values for the Norton equivalent. So then, using the equations from the previous page, the Norton resistance is VOC over ISC, 45 over 1.6 repeating gives us 27 ohms. And the Norton current is just the short circuit current, so that's 1.6 amps, 1.6 repeating amps. That allows me to draw the equivalent circuit. And so we have a Norton source, 1.6 repeating amps, and then a parallel Norton resistance of 27 ohms, and we're done. If I want to write the expression or draw the graph for this, I can plug it into the characteristic equation arranged for the Norton equivalent. And so I is negative 1 over Rn times the voltage plus our Norton current. And so just substituting those in, I get I is negative 0.037 Siemens times the voltage plus 1.6 repeating amps. And that would be the characteristic equation of the network. One last thing. If now I decided that I would rather have a Thevenin equivalent instead of a Norton equivalent, I have all the values I need to do that, but I could just go directly using from Norton to Thevenin using our relationships that we determined just previously. So the Thevenin resistance is equal to the Norton resistance, so that's 27 ohms, and so same resistance, just in a different configuration. And the Thevenin voltage is going to be the Norton current times the resistance that both of them share. Thevenin or Norton, I just chose to use Norton here as a subscript, it doesn't really matter. And so 1.6 repeating amps times 27 gives us our 45 volts, and there it is. And we had solved the open circuit voltage already, so we knew that was 45 volts anyway, so that all makes sense. All right, thanks for watching.